Our next conic section that we'll look at are parabolas. So let's explore parabolas in more detail. We're going to see that it involves a little bit more parts than what we're used to seeing when solving quadratic equations. First of all, when you look at this diagram here, you'll notice that we have an upwards facing parabola. I'll draw it with arrows so you're aware of where the parabola is. Okay? And then we also have our x-axis and y-axis. Now there are a couple of new things that you'll see here. Specifically, there's this point here, which we call 0p. This point is called the focus. And that focus is contained inside the parabola, and it kind of has that parabola wrapped around it. Another important characteristic that we'll see with parabolas is that there's this horizontal line that you see down below the x-axis, which we call the directrix. And this directrix, because it's horizontal, actually has the equation y equals negative p. Now, if you notice, the p's are actually the same values. That kind of shows you that from any point on the parabola, you can go a certain distance up to the focus, and then you also can go the same distance down to the directrix. So this is a distance of p. It turns out that if you go anywhere along the parabola, let's say this point here or this point here, that wherever you go, you'll always have a distance that is from the focus to that point on the parabola, which will actually always be the same distance as from that point to the directrix, in that that distance is perpendicular to the directrix. So I can do the same thing over here, right? I can show that this distance, let's show it with a geometry congruent mark there, is the same distance as this distance here, which is perpendicular to our directrix. Okay, so basically the idea here is that if I take any point, let's call this point over here the point x comma y, I can take any point along the parabola. I can always measure its distance from that point to the focus. And that distance is going to be the same distance as from that point on the parabola, perpendicular to the directrix. And I'll show that they are congruent by, again, showing those two congruent marks there. Okay. Now, in terms of how we can actually prove this using the parabola equation, let's go ahead and break up these parts that we've drawn into smaller parts. Okay, so the idea here is if we're talking about a distance, we're trying to find the distance from the focus to a point on the parabola, and we want to compare that with the distance from that point to the directrix. Now, one thing that you maybe will see here, hopefully you'll see this, is that you can actually draw a horizontal line and develop a right triangle here. Okay, so we actually have parts of right triangles. We can use characteristics of right triangles to represent this distance. Now we know that in a right triangle, based on this point, which we have classified as xy, that must mean that we are going from the point 0, 0, we are going horizontally a distance of x, which also means that the base of the triangle is also a distance of x. Those are congruent to each other. In addition to that, we also see that we're going up y units. So this entire distance right there is a distance of y. Okay. Now, since the triangle technically started at 0p, that must mean that this little piece, which is congruent to the other side, is also a distance of p, which means that technically on the right triangle, the distance that we're really trying to find here, this distance right here, the height of the triangle, is a distance of y minus p. Well, using the Pythagorean theorem, what we can say is that on this right triangle, that x squared plus the side b, which is technically y minus p squared, is equal to our hypotenuse. And our hypotenuse is actually going to be the length of that distance. So we'll call that c squared. So if we actually want to find distance, distance is technically just the value of c. So let me actually say that this is the distance from our focus, 0p, to the point xy. Okay? And if we really want to find the distance, then what we have to do is actually take the square root on both sides because we really just want the value of c. Now keep in mind when you do take the square root on both sides, you do get a positive and negative square root, but we know that because we're looking for distance, it really is just the positive value, so square root of x squared plus y minus p squared. Okay, so far what we found is basically this distance from the focus to that point xy. Now what are we comparing that to? Recall how we said that that distance is actually the same from the point on the parabola down to the directrix. What is that entire length? The entire length from that point xy straight down to the directrix, you can see it actually makes up the value of y, but then you have this additional length here going from that vertex straight down. That's a distance of p. So what we need to do is find that total distance. That distance is actually equal to y plus p. Okay, so this becomes a new equation that we can then solve for. So let's rewrite it again. What we have is the square root of x squared plus y minus p, quantity squared, is equal to y plus p. Now in order to solve this equation, we do need to get rid of the square root. So how do we get rid of square roots? We can square both sides. So if we square both sides, we end up getting, on the left side, the square root and square cancel out. And so now what we're left with is x squared. And while I'm at it, I'm actually just going to go ahead and simplify that y minus p squared as well. So that becomes plus y squared minus 2yp plus p squared is equal to y plus p squared. Again, we can multiply that through. That becomes y squared plus 2yp plus p squared. And then from here, we'll combine like terms. So if we bring the y squared over, what you'll notice is that they will actually cancel out. Now we don't have any more y squared. If we bring the p squared over, again, they cancel out. So we'll get rid of those. And then if we bring the negative, or if we bring the 2yp over to the other side, or actually, sorry, let me rephrase that. Let's bring the negative 2yp over to the other side. So what we'll end up getting is all on the left side, all we're left with is x squared, and on the right side, we are left with 4yp. Okay? So the more traditional way that you're probably used to seeing this is if you isolate y, you can basically divide both sides by 4p. And so what you end up seeing is that y, isolated, is equal to 1 over 4p x squared. Okay, so as you can see, that 1 over 4p, it kind of acts like almost like a coefficient of your x squared. You have your equation in the form of y equals x squared, basically, but now you'll see that there's kind of like this yellow box around 1 over 4p. You haven't really seen that before. Just kind of giving you a quick example here. You know, if you are normally used to seeing that you have an equation y equals x squared, typically you would have seen, oh, well, that's just a parabola, parent function, normal parabola, right? You think nothing of it. But really what's behind the scenes is that you have a 1 over 4p there. What is that saying? Well, technically that 1 over 4p was acting like a value of 1. So if you actually solve for that p value, you can see that the p is equal to 1/4, telling you that technically on a parent function parabola that the focus is going up by 1/4. It has a focus at the point 0, 1/4. That's for the parent function of a parabola. Okay, but now you can actually associate that 1 over 4p as being kind of like part of that coefficient. Okay, so you have two ways that you can write this. You can write it as y equals 1 over 4p x squared, or you can also write it as 4py is equal to x squared. It depends on kind of like the problem at hand. You might want to just work with any one of those equations there. Okay. So going on to the next page here, what we see here is that we have two different kinds of parabolas. We've already talked about the first one, and in this equation, or this parabola rather, This is where we have the equation x squared equals 4py, or you can think of it as y equals 1 over 4px squared. Any one of those forms would be acceptable. Remember, what that means is that for any parabola in which you have a point where you can call xy along the parabola, that's just telling you that this p-value is finding you the focus, and that focus is at the point 0p, and the directrix would then just be at the horizontal line, y is equal to negative p. Now you can do the same kind of proof for a horizontal parabola, but because it is horizontal, just keep in mind that you are kind of like finding the inverse, and so therefore, if you normally would have had x squared equals 4py, a horizontal parabola would then give you y squared equals 4px. If you did want to rewrite it so x is isolated, you could call that x is equal to 1 over 4p y squared as well. Again, any one of those equations would be acceptable to use depending on the circumstances. Keep in mind that these two functions that you see here, that's telling you that you kind of have that parent function, that positive coefficient, and if that's the case, then you do have your parabola facing in the right direction. It's facing right, versus, over here we have the x squared that's facing up. So do be aware that if you end up getting, like, let's say a negative in here, you know that you're actually going to have to flip that. You're going to have a parabola facing in the left direction. Okay, so I just want you to be aware of that. All right, so let's go ahead and now label the parts of this. If we know that, again, a parabola has a point at x comma y, now if this were our y-axis and x-axis, we can see now that the focus is actually, again, still contained within the parabola. It's the parabola is wrapped around the focus, and now the focus has a different point. You can see it still moves p units, but as an ordered pair, it's not going to be 0p anymore. Now it's going to be p comma 0. And the directrix is no longer a horizontal line, but rather a vertical line. So rather than being y equals, we have to call this x equals. And since it's on the other side of the y-axis, that would be x equals negative p. So those are just some basic characteristics of parabolas involving the focus and directrix with the value of p.